Question 1. Find the set of values of the constant k for which the quadratic equation 3kx squared plus k plus 8 times x plus 3 equals 0 has two distinct real roots. Okay, the fact that they are referring to the roots of the equation and two distinct roots, that means that the discriminant delta for this quadratic equation is greater than 0. So we have the quadratic equation in standard form as it is. So all we need to do is just find an expression for delta. Delta equals b squared minus 4ac. The value of b is the coefficient of x, which is k plus 8. The value of a is the coefficient of x squared, which is 3k. And the value of c is the constant, which is 3. So expanding this all out, k squared plus 16k plus 64 minus 12 times 3k, that's going to be minus 36k. So delta equals k squared minus 20k plus 64. Now, they want to know what the values of k need to be in order for this quadratic equation to have two distinct real roots. So we're going to take this expression for delta and make it greater than 0. For real roots, delta is greater than or equal to 0. But in this case, we're only considering delta greater than 0 because they want two distinct real roots. That means that the roots are not equal. If delta equals 0, we have two equal roots. So we are looking for two distinct or two unequal real roots. So delta is greater than 0. So k squared minus 20k plus 64 is greater than 0. Can factorize. That'll give us k minus 4, k minus 16. The critical values are k equals 4 and k equals 16. We can continue solving this inequality algebraically. It might be easier to do it graphically. This is a quadratic function whose x-intercepts are 4 and 16. So those are the critical values. The axis of symmetry will be at k equals 10. It doesn't really matter. We just want to know what the function is going to look like. So we're looking for values where the function is positive, the y values are positive. In other words, where does the function lie? Above the x-axis. That happens to the left of 4 and to the right of 16. So the solution to the quadratic inequality is k is less than 4 or k is greater than 16. And for those values of k, if k is less than 4 or k is greater than 16, then this quadratic equation will always have two distinct real roots. We can test it by actually sketching functions, quadratic functions, with these values of k to illustrate that you always have two distinct real roots. Here are three different variations of the quadratic have been sketched. First quadratic, the red quadratic, has k equal to 3, and the solution was k is less than 4 or k is greater than 16. When that is the case, this quadratic over here will have two distinct real roots. So 3 is less than 4. So when k equals 3, we get the quadratic y equals 9x squared plus 11x plus 3. And we can see the red function clearly has two x-intercepts. Equation 2, the blue quadratic, has k equal to 20, which is clearly greater than 16. And again, the blue quadratic has got 2 x-intercepts. And then the last quadratic, the green quadratic, is a value between 4 and 16. In this case, I chose a value of 10. And you can clearly see that the green quadratic does not cut the x-axis at all. It clearly lies above the x-axis, which means there are no x-intercepts. And this basically confirms the solution is correct. Question 2. A geometric progression has a first term of a and a common ratio cos theta, with theta as an angle in radians between 0 and pi by 2. It's given the second term is 8 and the fifth term is an eighth. Find the value of theta, give your answer correct to 3 significant figures. Okay, so we have a geometric progression. The first term is a and the common ratio is cos theta. The second term is 8 and the fifth term is an eighth. So we're going to take the expressions, the general expression for the second and fifth term of a geometric progression. So respectively, the second term is AR, so AR equals 8, and the fifth term is AR to the 4, and that equals an eighth. We now just need to solve for, we're given that R equals cos theta. The first thing we're going to do though is just divide these two expressions. AR to the 4 divided by AR is going to be an eighth divided by 8. This gives us R cubed equal to 1 over 64. R is therefore going to be the cube root of that, which is a quarter. So they tell us that the ratio R is cos theta. So now cos theta equals a quarter. And now we just find the value of theta by performing the inverse function. So theta is shift cos a quarter, and make sure that your calculator is in radians. So theta equals 1.318 to 3 significant figures. Theta will be 1.32 radians. We are now required to find the exact value of the sum to infinity. Exact meaning no decimals in our answer. So this sum to infinity is a over 1 minus r. Now we know that cos theta equals a quarter. We're not going to use the approximate value of theta here because the question is asking us to find the exact value. That means we have to use exact values. So we're not going to use any decimals whatsoever. So we have to use this construct for r, for cos theta. So we are going to now evaluate the sum to infinity, which is a over 1 minus r, which is cos theta. But before we do that, we do need to know what the value of a is. And we know that a, the second term, AR, equals 8. So a times cos theta equals 8. A is 8 over cos theta. We can now plug this into the sum to infinity, which is 8 over cos theta, that's a, over 1 minus r, 1 minus cos theta. We can simplify that as 8 over cos theta times 1 minus cos theta. So that equals 8 over a quarter times 1 minus a quarter. That's 8 over a quarter times 3 quarters. 8 over 3 over 16. It's 128 over 3. And this is an exact answer. Question 3. In the expansion of px plus 3 to the power of 5 minus x cubed plus p of x to the power of 4, the coefficient of x to the 4 is 216. We are required to find the value of the positive constant p. Okay, so we're going to just expand this in parts, just to keep it as simple as possible. So we're first going to expand px plus 3 to the 5, which is 5 choose 0 times px to the 5 plus 5 choose 1 px to the 4 times 3 to the 1 plus 5 choose 2 px to the 3 times 3 squared. Now we can continue expanding, but just bear in mind that we are told the coefficient of x to the 4 in this entire expansion over here is 216. So we only need to concern ourselves with terms that contain an x to the 4. Now we've gone beyond that. This term over here contains x to the 4. When we expand this binomial any further, this expression any further, we're going to get x squared, then we're going to get x. So we're not going to get another x to the 4 term. So there's no need to continue expanding this binomial. So we're going to stop here because this is all we need. We need that particular term. We're now going to expand this expression here. So that equals 4 choose 0, x to the 3 to the 4, plus 4 choose 1, x to the 3 to the 3, times p over x to the 1, plus 4 choose 2, x to the 3 squared, times p over x all squared, plus 4 choose 3, 1 times p over x to the 3 plus, and then the last term. Now, we're not going to continue expanding here because, again, we're looking for a term that contains only x to the 4. So the first term here is x to the 3 to the 4, which is x to the 12. So that's a term we don't need. The second term has x to the 3 to the 3, which is x to the 9, divided by x is x to the 8. That's also not a term that we need. The next term, however, is x to the 3 squared, which is x to the 6, divided by x squared will give us x to the power of 4. So this is a term that will give us a term in x to the 4. And just to check, the very next term is x to the 3 divided by x to the 3, which gives us a term not in x. So therefore, we're not going to expand any further. We've got the two terms that we require. So now we are going to identify the coefficient of x to the 4 in each of these terms. Now I have to consider, I'm just going to first write this expansion out fully just so we don't make any mistakes. So we start with the expansion of px plus 3 to the 5 will be all of this in pink. So px plus 3 to the 5 minus x cubed plus p over x to the 4 will be, I'm not going to add all the terms that we don't need, we're just going to put an ellipsis there, plus 5 choose 1 px to the power of 4 times 3 plus, and then we'll just put another ellipsis there, minus this entire expansion in purple, and plus the term we need, 4 choose 2 x to the 3 squared times p over x all squared, and then the ellipsis, and we can close that bracket. X to the 4 will be 5 choose 1 e to the 4 x to the 4 times 3 minus 4 choose 2 x to the 6 times p squared over x squared. 5 choose 1 is 5. 5 times 3 is 15. So 15 p to the 4 x to the 4 minus 4 choose 2 is 6. Have p squared x to the 4. So the coefficient of x to the 4 is 15 minus 6p squared. And the coefficient of x to the 4, we are told, is 216. So we're going to equate this entire expression to 216. 15p to the 4 minus 6p squared equals 216. Now take the 216 across to the left so that we can get a quadratic. Divide through by 3 to simplify. 5p to the 4 minus 2p squared minus 72 equals 0. You can use a substitution here if you'd like. It's not necessary. This will factorize as 5p squared and p squared as the first terms in the brackets. We'll then have 18 and 4 as our factors of 72. So 5p squared plus 18 equals 0. This is impossible because p squared is a positive number. It's always positive regardless of the value of p. 5 times that positive number is still positive. You add 18, it's still positive. 5p squared plus 18 will therefore never be equal to 0. So there's no solution to this equation. If p was 0, you would still have 0 plus 18, and 18 is still greater than 0, and clearly not equal to 0. So there's no solution to this equation here. Or p squared minus 4 equals 0. P plus 2 times p minus 2 equals 0. P equals minus 2, or p equals 2. They did say that p is a positive constant, so therefore we invalidate p equals negative 2. If you do not invalidate solutions, you will be penalized. Cambridge will penalize you. You'll lose unnecessary marks as a result. So always check your answers. So p equals 2. Question 4. Express 1 minus 6x minus x squared in the form a minus x plus b all squared, where a and b are constants. The first thing we're going to do is just rearrange this as minus x squared minus 6x plus 1. We're going to be completing the square to get the quadratic in that particular form there. We'll then rearrange, do whatever we need to do to make it, to put it into this particular form. Let's stick to a convention with how you learned how to complete the square, and stick with that. Regardless of how the question is actually phrased, stick to what you know and work with that, and then arrange the expression in the form that it's required to be in. So the first thing we do is we take out a negative 1 from all the terms, because we need to ensure the coefficient of x squared is positive 1. So we take out a minus, and we're left with x squared plus 6x minus 1. Now add a bracket squared, minus 1, and then minus the same bracket squared. Inside that bracket is half the coefficient of x. Half of plus 6 is plus 3. So plus 3 goes into both brackets. First three terms here inside the square brackets will give us a perfect square trinomial, x plus 3 squared. So just to highlight that, we're going to take x, is there, and whatever we put inside that bracket will then so appear as the second term inside that perfect square trinomial. Then we have minus 1 minus 3 squared is 9. That equals minus x plus 3 all squared minus 10. And now we bring the minus sign into the square brackets. So minus x plus 3 all squared plus 10. And just to put it into the form that they required, they wanted in the form a minus x plus b all squared. We are going to have 10 minus x plus 3 all squared. So clearly a equals 10 and b equals 3. Graph of y equals x squared. Let's just call this f of x. It's just easier to refer to. F of x equals x squared is transformed to the graph of g of x equals 1 minus 6x minus x squared by reflection followed by translation of the vector mn. Give details of the reflection and determine the values of m and n. Okay, so we've got the function f of x equals x squared. Now we're just going to write this in turning point form. The reason we had to express the previous question in the form that we did was leading up to this particular question. So we'll start with g of x. G of x is minus x plus 3 all squared plus 10. Now we're going to write f of x in a similar form. F of x equals x minus 0 all squared plus 0. Now the first thing we need to notice is that the coefficient of the squared term in f of x is positive 1. The coefficient of the squared term in g of x is negative 1. Now that positive negative indicates that there is a reflection about the x-axis because the y values have actually changed. Let's, for example, say that let's just call it h of x, just so we don't confuse it with this. If we had negative x squared, h of x is negative x squared, and f of x is positive x squared. You can clearly see that the coefficient of x squared in f of x is positive 1, and in h of x it's negative 1. That means that there's a reflection about the x-axis. So the first thing, the reflection is about the x-axis, right? So f of x equals x squared would be reflected about the x-axis to give h of x, which is minus x squared. From that point there, we would then transform it to g of x by performing a translation by the vector mn. So that translation would be a shift to 3 units to the left. So this would be a horizontal shift of 3 units to the left, followed by a vertical shift of 10 units up. So the vector, in other words, will be minus 3, 10. So let's go back. If we have the function f of x equals x squared, if we perform the reflection about the x-axis, we change the sign of y. The sign of y is positive in f of x, so change to a negative and we get h of x. So that'll be a reflection about the x-axis because we changed the sign of y. We then took h of x and performed a vector translation, and that vector translation was to shift the function 3 units to the left and 10 units up. And that is the vector minus 310. Just to be clear, a function in turning point form, a quadratic function in turning point form, is y equals a times x minus p all squared plus q. In this form, the turning point of the function is pq. If p is positive, then we get a shift to the right, however many units as the value of p. And if p is less than 0, we get a shift to the left, however many units of p as the value itself. If q is greater than 0, we get a vertical shift up, the number of units is q. If q is less than 0, then we get a shift down. And these shifts are vector translations. 5. Show that tan to the 4 theta minus 1 equal to 1 minus 2 cos squared theta over cos to the 4 theta. Okay, well, let's start with the left-hand side. There's a whole host of ways we can go about proving this identity. Let's just start with the left-hand side because we can express tan in terms of sine and cos. So the left-hand side will be sine to the 4 theta over cos to the 4 theta minus 1. In a single fraction, we'll have sine to the 4 theta minus cos to the 4 theta over cos to the 4 theta. Now, if we look at the right-hand side, we've only got cos on the right-hand side. Yes, it's cos squared and cos to the 4, but the point is the trig ratio is only cos. We have sine to the 4. We've got sine and cos. We now need to ensure we only have the trig ratio cos. So we are going to use the square identity, sine squared theta plus cos squared theta equals 1. We're going to write sine to the 4 as sine squared theta squared minus, and then minus cos to the 4 theta over cos to the 4 theta, just coming up here. This sine squared we're going to write as 1 minus cos squared theta. That is squared. Then subtract cos to the 4 theta, and that's all over cos to the 4 theta. We can now square out and FOIL out this bracket, so we have 1 minus 2 cos squared theta plus cos to the 4 theta minus cos to the 4 theta, that's all over cos to the 4 theta. Cos to the 4 theta minus cos to the 4 theta is 0, and we have 1 minus 2 cos squared theta over cos to the 4 theta, which equals the right hand side. Hence, solve the equation. Cos squared theta times 10 to the 4 theta minus 1 equals 7. For theta is an angle between 0 and 180 degrees. Okay, the fact that the question says hence means use the previous results to solve this. So we're just going to write it down as it is. Now we're going to manipulate this until it looks like what we had in the previous question. The previous question was show that 10 to the 4 theta minus 1 is 1 minus 2 cos squared theta over cos to the 4 theta. Now, looking at this expression here, bear in mind we can only solve a trigonometric equation working with a single trigonometric ratio. We've got cos and tan, that doesn't help us solve the equation. So we are first going to write this as 10 to the 4 theta minus 1 equals 7 over cos squared theta. The first thing we do is put it into this form, 10 to the 4 theta minus 1, because we know that it is equivalent to that expression, 1 minus 2 cos squared theta over cos to the 4 theta. So 1 minus 2 cos squared theta over cos to the 4 theta equals 7 over cos squared theta. Now we've only got a single trig ratio here, cos, which means we manipulate and solve. So cross multiplying cos squared theta times 1 minus 2 cos squared theta equals 7 cos to the 4 theta. Multiplying in cos squared theta minus 2 cos to the 4 theta equals 7 cos to the 4 theta. All terms over to one side. The other side equal to 0 gives us 9 cos to the 4 theta minus cos squared theta equals 0. We can divide through by take out rather cos squared theta as common factor. So cos squared theta times 9 cos squared theta minus 1 equals 0. Now we can just solve cos squared theta equals 0 or cos squared theta equals 1 over 9. So cos theta equals 0. Cos theta equals 0 is not a valid solution, and the reason is, if we look at this equation over here, we're given cos squared theta times 10 to the 4 theta minus 1 equals 7. We rearrange this as 10 to the 4 theta minus 1 equals 7 over cos squared theta. We then used, from the previous question, to solve for theta, 1 minus 2 cos squared theta over cos to the 4 theta equals 7 over cos squared theta. That's how we formulated this quadratic over here. Now, the denominators in both left and right hand side, cos to the 4 theta, cos squared theta. Cos theta may not be equal to 0, because if cos theta is 0, cos squared and cos to the 4 theta also 0, and division by 0 is undefined. So that is our restriction. So that's why cos theta equals 0 is not applicable. So the only solution will be cos theta equals plus or minus 1 over 3. We now establish a reference angle. Theta will be 70.5 degrees. Now, the domain is theta is between 0 and 180. So if we look at the cast diagram, we're looking at these two quadrants, quadrant 1 and quadrant 2. So the first solution, because we're considering cos theta is plus or minus a third, cos is positive in the first quadrant and it's negative in the second quadrant. So the first solution will be theta is 70.5 degrees, and the second solution will be, in the second quadrant, 180 minus 70.5. So theta will be 109.5 degrees. So those are the two solutions. Question 6. Functions f and g are defined by f of x equals x plus 3 all squared minus 12 for x is greater than or equal to 0, and g of x is 2x minus 5 for x is a real number. State the range of f. Now, if we just first consider f of x if there was no restriction on the domain. If x was an element of real numbers or no restriction was actually stated, this is the restriction that they've stated in the problem. But let's just consider for a second that there is no restriction. The turning point is minus 3 minus 12 of this function. Again, we don't really care too much about the accuracy of the function. We just want to get an idea. So minus 3 minus 12. Turning point is there. And the function shapes up because the coefficient of the squared term a is positive. So the function shapes up. So we're just going to get a function that looks like this. Again, we don't care too much about the accuracy of the graph. We just need to get an idea what it looks like. This that's been drawn here is the function f of x if there was no restriction on the domain. And if that was the case, let's just the range of this function depends upon the turning point. Now, the function f of x does not go beyond y equals minus 12. That means that y is greater than or equal to minus 12, or f of x is greater than or equal to negative 12. But we've restricted this domain saying that the function exists for x is greater than or equal to 0. X is a positive number or 0. So we have to sketch the function such that we consider this domain. Now the function f of x equals x plus 3 all squared minus 12 for x is greater than or equal to 0. So basically we need to know where the function starts when x does equal 0. So f of 0 will be 0 plus 3 all squared minus 12. That will be 9 minus 12, which is minus 3. So the function starts at minus 3, which is there. And the y values continue to get more and more positive as x becomes more positive. So your range of f will therefore be y is greater than or equal to negative 3, or f of x is greater than or equal to negative 3. Find an expression for the inverse of f. So f of x equals x plus 3 all squared minus 12. Now, when you're looking for the inverse of a function, remember that the inverse of a function only exists if the function itself, f, is 1 to 1. This function f is 1 to 1, as we saw in the graph, because the range, sorry, not the range, the domain was restricted. Because the domain was restricted, we have a 1 to 1 function. Because of the existence of that 1 to 1 function, the inverse of f will exist. So, to find the inverse function now, we're going to switch x and y around. So x equals y plus 3 all squared minus 12, and we proceed to solve for y. So x plus 12 equals y plus 3 all squared, square root both sides, plus or minus root x plus 12 equals y plus 3, y equals minus 3, plus or minus root x plus 12, and therefore f to the minus 1x will be minus 3 plus root x plus 12. We consider it's not your y values. Minus 3 minus root x plus 12 will be negative. We have to consider only positive y values because of the nature of the function and the restriction placed upon f. Now required to solve the equation g of f of x equals 69. So g of f of x equals 69. G of f will be g of x plus 3 all squared minus 12. That equals 69. In g of x, wherever we see an x, we're going to replace it with x plus 3 all squared minus 12. So we'll have 2 times x plus 3 all squared minus 12 minus 5 equals 69. 2 times x plus 3 squared minus 12 equals 74. X plus 3 all squared minus 12. 3 all squared equals 49. X plus 3 equals plus or minus 7. X is minus 3 plus or minus 7. X is minus 3 plus 7 is 4. Or x is minus 3 minus 7 minus 10. Now, x has to be positive, greater than or equal to 0, so we invalidate x equals minus 10, and the only solution is x equals 4. The diagram shows a sector of a circle with center O and radius r centimeters. The shaded region is bounded by the chord AB and the arc AB. The size of angle AOB is 2 pi by 3 radians. Show that the area of the shaded region is approximately 0.614 r squared. So first, let's identify how we are going to find the area of the shaded region. The area of the shaded region will be the area of the sector AOB minus the area of triangle AOB. The area of a sector is a half the radius squared times the arc angle. So the area of sector AOB will be a half, the radius is r, a half r squared times the sector angle, which is 2 pi by 3. Okay, then minus the area of triangle AOB. To get the area of triangle AOB, we're going to use the area rule, so it's going to be a half r times r sine of the included angle, which is 2 pi by 3. So that will equal, those 2's will cancel. We'll have pi r squared over 3 minus a half r squared sine 2 pi by 3. 2 pi by 3 is in degrees 120 degrees. Sine 120 is the same as sine 60, which is root 3 over 2. That's pi r squared by 3 minus root 3 over 4 r squared. We can take out a common factor of r squared, and we have in the brackets pi by 3 minus root 3 over 4. And we can now calculate pi by 3 minus root 3 by 4, which is approximately 0.614. 0.61418. We're going to round that up to 0.614, which is exactly what they were looking for. Now, given that the radius of the circle is increasing at a rate of 0.4 centimeters per second, we're required to find the rate of increase of the area of the shaded region at the instant when the radius is 20. Okay, so we are given that the radius of the circle is increasing at a rate of 0.4 centimeters per second. Now, whenever you see the word increase or decrease and rate, your mind needs to automatically go to differentiation. What increase and decrease? An increase or a decrease always implies change. If something is increasing or decreasing, it's clearly changing, right? And the word rate refers to per unit time. So in calculus, change is d, and the rate of change is d dt. This construct, this differential, is the rate of change. That's what rate of change is. So the fact that the radius is increasing at a rate means that the radius is changing. So we are talking about how the radius is changing, how it's increasing. The rate at which the radius increases is 0.4 centimeters per second. So we're given the differential dr dt. We are required to find the rate of increase of the area of the shaded region. So we are looking for the rate of increase of the area. The area is increasing, the area is changing, at a rate. Therefore, we are required to find the differential dA dt at the instant when the radius is 20. So we need to find the differential dA dt when r equals 20. Now, in order to relate these two differentials, we need a third differential, and that will come from dA dr, the rate at which the area is changing with respect to the radius. Now, since we know that the area of the shaded region, so we'll just indicate it like that, with respect to r, well, we know that the area is 0.614 r squared. That's what we had in the previous question. So to find the rate of change of the area of the shaded region with respect to the radius, we're going to differentiate this function. So dA dr will be 0.614 times 2, which is 1.228 r. Now we're going to relate these three differentials together. So since we're looking for the differential dA dt, we'll start with that. So dA dt equals, now we need, if you look at this construct, this differential dA dt, we have dA in the numerator and dt in the denominator. So we need to have the equivalent on the right-hand side. So we're going to have to start with dA, but we've got to use a different differential. And that differential we're going to use is dA dr. So we have to use dA dr. And now we need to eliminate this dr, because as you can see on the left-hand side, we have dA dt. There is no dr. So we have to eliminate dr. So we're going to multiply by dr, so the dr's will essentially cancel. And we need dt in our denominator, so we are going to divide by dt. When we simplify the right-hand side, we get the differential dA dt. dA dr, we have an expression for 1.228r. dr dt we know is 0.4. So dA dr is 1.228r, and dr dt is 0.4. That equals 0.4912r. We now need to evaluate this differential dA dt when the radius is 20. So that equals 0.4912 times 20, which is 9.824. If you want the units, you can add that as well. It's the rate of change, the rate of increase of the area, which is centimeters squared per unit time, so it's per second, or times s to the minus 1. Now I need to find the rate of increase of the length of the arc AB. Give your answer correct to two significant figures. We want the rate of increase of the length of the arc AB. So we're looking for increase implies change. Length, we'll just call that, we normally use the letter S for arc length, so we're just going to use S again. So we're looking for ds, and rate is dt. So ds dt is what we want here. So we need an expression now for the arc length AB. Clearly we need an expression for the arc length. S equals r theta. So S equals r times this theta here is the arc angle, which in this case is 2 pi by 3. We now are going to find a differential ds dr, because we have to find the differential ds dt. So ds dr will be 2 pi by 3 is a constant, and the derivative of r will just be 1. So ds dr is 2 pi by 3. And we know that dr dt is 0.4. How did we know to use this differential? Well, look at the differentials that we have, ds dt and ds dr. The only thing that we need to relate now is dr to dt, which we know was 0.4. That was given to us. So ds dt equals ds dr times dr dt, and that will be 2 pi by 3 times 0.4, which is 4 pi by 15, which is 0. To two significant figures, 0.8377, 0.84. Question 8. The diagram shows the curve of the equation y equals half root x and the point P with coordinates 9, 3 over 2. The shaded region is bounded by the curve and the lines x equals 0, which is the y-axis, and y equals 3 over 2. Find the area of the shaded region. Okay, so to find the area of the shaded region, we're going to be integrating between x equals 0, so the origin, and x equals 9, which is the x coordinate of point P. So the area of the shaded region will be the top curve, which in this case is y equals 3 over 2, minus the bottom curve, which is y equals a half root x. So we will have 3 over 2 minus a half root x, and we are differentiating, rather integrating with respect to x. That equals 3 over 2 times x minus a half, x to the half plus 1, so it's x to the 3 over 2. Then we multiply by 1 over 3 over 2. And this is evaluated between x equals 0 and x equals 9. That equals 3 over 2 times 9 minus a third times 9 to the 3 over 2 minus, we don't have to do this, when x equals 0, then both of these terms are just going to fall away, so we don't have to write that all out. That's 27 over 2 minus a third times 9 is 3 squared. 3 squared to the 3 over 2 is 3 to the 3, which is 27. So 27 over 2 minus 27 over 3 is 9. 27 over 2 minus 9 is 9 over 2. So that is the area of the shaded region. The shaded region is rotated 360 degrees about the y-axis, and we're now required to find the exact volume of the solid produced. So we've got the shaded region, and we are now reflecting about the y-axis, and we are rotating the shaded region about the y-axis. In other words, we are going to have circular cuts that will be parallel to the x-axis. We have this curve here, which is y equals 3 over 2, and the curve we're given is y equals a half root x. Now, since we are rotating about the y-axis, we will be integrating with respect to y. In other words, these functions need to be expressed in terms of y. This curve y equals a half root x is y expressed in terms of x. We now need to manipulate this and make x the subject. So the first thing we're going to do, multiply both sides by 2, so 2y equals root x, and now we square both sides, so 4y squared equals x. X equals 4y squared is the curve that we're working with, and now the point here, which was P, is 9, 3 over 2. We are now, our limits, our boundaries of integration will be, which is y equals 0, and we are integrating between 0 and 3 over 2. So y equals 0 and y equals 3 over 2 are the boundaries of integration. Since we're looking for volume, volume is area times height. So essentially what we are doing to find the volume, we look at the circular cuts, the cross-sectional cuts of the region, and that gives us a circle. Those circular cuts are circles, and the area of a circle is pi r squared. So we know that the area is pi r squared. So that gives us the area, but for the volume we need the height or the thickness of each of those cuts. right? And that is going to be dy. dy represents the thickness of the cut. So integrating between y equals 0 and y equals 3 over 2 pi r squared dy. The pi is a constant, so we can actually pull it out of the integration. Yes, the radius is 4y squared. So the integral from 0 to 3 over 2. R is 4y squared, but r squared is therefore 4y squared squared, and we integrate with respect to pi. Integral from 0 to 3 over 2. That's 16y to the 4 dy. Now we can finally integrate. So we'll have 16y to the 5 divided by 5 from 0 to 3 over 2. That's pi times 16 times 3 over 2 to the 5 over 5 minus, now when y equals 0, 16y to the 5 over 5 is just going to be 0, so we're just going to subtract 0. The volume is 243 pi by 10. Now what's the exact volume? So this is how we give our answer. Question 9. An arithmetic progression has a first term of 2 and a common difference d. The sum of the first n terms is denoted by s subscript n. It's given that the sum to 2 terms minus 1, the sum to 4 terms, and the sum to 9 terms are the first 3 terms of a second arithmetic progression. Find the value of d. Okay, so we have an arithmetic progression. The first term is 2 and the common difference is d. The sum of the first n terms is Sn. Okay, so we know that the sum to 2 terms minus 1 of this arithmetic sequence, the sum to 4 terms, and the sum to 9 terms then form the first 3 terms of a second arithmetic progression. So we're going to find expressions for the sum to 2 terms minus 1, the sum to 4 terms, and the sum to 9 terms. So the sum to 2 terms minus 1, the sum to n terms of an arithmetic progression is n over 2 times 2a plus d times n minus 1. The sum to 2 terms will therefore be 2 over 2 times 2a, a equals 2, so 2 times 2 is 4, plus d times n equals 2 in this case. 2 minus 1 is 1, so that's going to be 1 times 4 plus d, which is just 4 plus d. Therefore, the sum to 2 terms minus 1 will be 4 plus d minus 1, which is d plus 3. So this term here, d plus 3, will be the first term of the second arithmetic progression. We're now going to proceed similarly to find the sum to 4 terms and the sum to 9 terms of the first arithmetic progression. So the sum to 4 terms is 4 over 2 times 2a, a equals 2, 2 times 2 is 4, plus d times, we're summing to 4 terms, n equals 4, n minus 1 equals 3. That equals 2 times 4 plus 3d, which is 8 plus 60. So the sum to 4 terms, this is now the second term of the second arithmetic progression, 60 plus 8. And finally, we find the sum to 9 terms. So the sum to 9 terms is 9 over 2 times 2a, a equals 2, 2 times 2 is 4, plus d times n, in this case is 9, 9 minus 1 equals 8. That's 9 over 2 times 4 plus 8d. That's going to give us 36 over 2, that's 18, plus 72 over 2 is 36d. So the sum to 9 terms is 18 plus 36d. So that's now the third term of the second arithmetic progression. Now that we have the first 3 terms of the second arithmetic progression, we can now solve for d. Now, arithmetic progression has a constant first difference, so that means that term 2 minus term 1 equals term 3 minus term 2. So 6d plus 8 minus d plus 3 equals 36d plus 18 minus 6d plus 8. So we'll have minus 25d equals 5. D is 5 over minus 25. D is minus a fifth. Hence find the difference between the values of the 15th terms of the two arithmetic progressions. So the first arithmetic progression and the second. So the first thing we're going to do is find the 15th term of each of these progressions. First arithmetic progression had a first term of 2 and a difference d. D is minus a fifth. So we want to find the 15th term, which is a plus 14d. That's going to be 2 plus 14 times minus a fifth. It's going to be minus 4/5. And for the second arithmetic progression, the first term was d plus 3 second progression. A is 14 over 5 and the common difference is 4. So the 15th term is a plus 14d. 14 over 5 plus 14 times 4. That's 294 over 5. The difference between the 15th terms of the two arithmetic progressions will be 294 over 5 minus 4 over 5 will be 298 over 5, which is 59.6. Question 10. A circle has equation x squared plus y squared plus 4y minus 21 equals 0, and a straight line has equation 2x plus y minus 8 equals 0. The line intersects the circle at 2 points. Find the coordinates of these 2 points of intersection. Now, whenever we're dealing with points of intersection, we're equating two expressions, right? We're equating, in this case, the circle to the function, the straight line graph 2x plus y minus 8 equals 0. So all we're doing is simultaneous equations. So the first thing we're going to do is just isolate y from the straight line. So y equals minus 2x plus 8, and we're now going to substitute that expression for y into the circle. So we'll have x squared plus minus 2x plus 8 all squared plus 4 times minus 2x plus 8 minus 21 equals 0. Gives us the quadratic equation x squared minus 8x plus 15 equals 0. So x equals 3 or x equals 5. These two values of x represent the x coordinates of the points of intersection. Now we need to find the y coordinates of these points. So we sub x equals 3 and x equals 5 into either of the equations, but we are going to choose the simpler one, which is the straight line. So y equals minus 2 times 3 plus 8. Y equals 2, so the first point of intersection is going to be 3, 2, and we'll call that point A. And then the second point, y equals minus 2 times 5 plus 8. Y equals minus 2, so the second point of intersection will be B, 5 minus 2. Illustrating it graphically, here's the one point of intersection, and there is the other point of intersection. So that B is the point, 5 minus 2, A is the point, 3, 2. The circle has center C and the 2 points of intersection are denoted by A and B, which you've already done. Find the area of triangle ABC. Okay, so we've marked points A and B. We now need to just find the center of the circle. So we are going to complete the square for both x and y to the right. So x squared plus y squared plus 4y equals 21. So we have x squared plus y squared plus 4y plus 2 squared equals 21 plus 2 squared. X squared plus y plus 2 squared equals 21 plus 4 is 25. So the center of the circle is 0 minus 2 and the radius is 5. 0 minus 2 is our center C, and now we can find the area of triangle ABC. Area of triangle ABC using the area rule will be a half AC times the length of BC. Just call this angle here theta, sine theta. Now, to find the area of triangle ABC, we're first going to need to determine the size of theta. So to do that, we're going to use the cos rule because we have got the coordinates of A and B, which means we can find the length of AB. We know that AC and BC are radii of that circle. So to find theta, we're first going to use the cos rule. So the cos rule states AB squared equals, now because we're looking for theta, we're going to use the side opposite theta, which is AB, square it, it's on its own on the left. AB squared equals AC squared plus BC squared minus 2 times AC times BC cos theta. We can use the distance formula to find AB. So AB equals the square root of x2 minus x1 all squared plus y2 minus y1 all squared. AB is the square root of 5 minus 3 all squared plus minus 2 all squared. That will equal the square root of 5 minus 3 is 2. 2 squared equals 4. Minus 2 is minus 4. Minus 4 squared is 16. 4 plus 16. So AB is the square root of 20. So we can mark that here. And we'll just leave it in this form. It doesn't really matter. We can leave it in unsimplified form. AB is root 20. So AB squared will be 20. AC is 5. 5 squared is 25. BC is also 5. 5 squared is 25. Minus 2 times 5 times 5 cos theta. 20 equals 50 minus 50 cos theta. 50 cos theta equals 30. So cos theta is 3 over 5. Now we could find theta. If we do shift cos theta, then theta is going to be approximately 53.1 degrees. We're not going to do that because we are going to find the area using a different method, and also for accuracy sake, we are going to evaluate and find a value for sine theta, an exact value for sine theta, and you'll see why. Let's use the value of theta, the approximate value of 53.1 degrees. So the area of the triangle will be a half AC, so it's going to be a half times 5 times 5 sine 53.1, and that's 9.996 plus change. That's approximately 10, right? And the reason we don't get exactly 10 is because we used an approximate value of theta. If we used all the decimal places of theta, we would have gotten exactly 10 for triangle ABC. Now, we're not going to use the approximate value for theta. We're going to use the exact value for the ratio sine theta. If cos theta is 3/5, then sine theta is 4/5. How we know that? If you draw a triangle, we'll just use the first quadrant because it's easier. If that is theta, then opposite of that, well, cos theta is 3/5, so adjacent will be 3, hypotenuse will be 5, and using Pythagoras' theorem, the other side, the opposite side of theta will be 4. So that's how we know that sine theta is 4/5. So that's going to be a half times 25 times 4/5. It's going to be 100 over 10, which is exactly 10. That is one way to find the area of triangle ABC. You can also drop a perpendicular from C to AB, right to the midpoint of AB. Call that point P, and then we can use half base times height. The area of triangle ABC will be a half base times height. So the height will be PC, base will be AB. So you'd have to first find the midpoint of AB, which will give you point P. So midpoint of AB will be x2 plus x1 over 2, 3 plus 5 over 2, y2 plus y1, so 2 minus 2 over 2, that'll be 4, 0, so P is the point, 4, 0. You can now use the distance formula to find the length of CP, use the distance formula to find the length of AB, and you can find the area. So the length of AB will be your base, and the length of PC will be the height of the triangle. Use the distance formula, and you will get the same answer of 10. And our AB is root 20, and PC will be the square root of 4 minus 0 all squared plus 0 minus minus 2, 0 plus 2 all squared. That's the square root of 4 squared is 16 plus 2 squared is 4, so that will be root 20. So PC is also root 20. So we will have a half times 20, which gives us 10. So we get exactly the same area as we did when using the area rule. Question 11. A curve passes through the point P, 4, 3, and is such that dy dx equals 8 over x squared minus 10 over 2x minus 3 all squared. Find the equation of the normal to the curve at P. Give your answer in the form y equals mx plus c. Okay, so what they've given us, dy dx, is the gradient function. And this represents the gradient of a tangent to a curve. So dy dx represents the gradient of a tangent to a curve. We need to find the equation of a normal. Okay, a normal is a straight line that is perpendicular to a tangent. So the first thing we need to do to find the equation of the normal, we obviously need to know the gradient of the normal and a point. We know what that point is because that point was given to us. It's P43. So all we need to do is find the gradient of the normal. But to find the gradient of the normal, we first have to find the gradient of the tangent to the curve at P. dy dx represents the gradient of a tangent to a curve. So at P, where x equals 4, you're now going to find the gradient of the tangent to the curve. That's going to be 8 over 4 squared minus 10 over 2 times 4 minus 3 squared. 8 over 16 is a half, minus 10 over 8 minus 3 is 5 squared is 25. So it's going to be a half minus 2 over 5. This now represents the gradient of the tangent to the curve at the point P, 4, 3. Therefore, the gradient of the normal to the curve at P is the negative reciprocal of 1 over 10, which is negative 10. We now have the gradient of the normal, and we have the point of contact. So we can now determine the equation of the normal. So 3 equals minus 10 times 4 plus c. C equals 43. Therefore, the equation of the normal is y equals minus 10x plus 43. Next, find the rate of change of the gradient of the curve when x equals 4. So the rate means per unit time, so dt. Change is, in calculus, represented by d, and the gradient is m. So we're looking for the differential dm dt. And this when x equals 4. Because the gradient is already represented by a differential dy dx, the rate of change of that gradient therefore means you're looking for the second derivative of the function. So dy dx equals 8x to the minus 2 minus 10 times 2x minus 3 to the minus 2. So the second derivative equals minus 16x to the minus 3 plus 20 times 2x minus 3 to the minus 3 times 2. So it's minus 16 over x cubed plus 40 over 2x minus 3 all cubed. And we want to know what the second derivative is when x equals 4. So it's minus 16 over 4 cubed plus 40 over 4 times 2 is 8 minus 3 is 5. 5 cubed is 125. So minus 16 over 64 plus 40 over 125 equals, that's 7 over 100, which is 0.07. Given that the curve also passes through the point minus 1q, find the value of q. Now, we are given an expression dy dx, which represents the gradient of a tangent to the curve. The curve passes through the point 4,3, but it also passes through the point minus 1q. So if we're required to find a point that lies on the curve, we're first going to need to know the defining equation of that curve. In other words, we need to integrate the expression dy dx to get the equation of the curve. So integrating this expression, eight x minus 1 divided by minus 1 minus 10 times 2x minus 3 minus 1 divided by minus 1, but also multiply by the derivative of 2x minus 3, so multiply by half, plus the constant of integration. So y equals minus 8 over x plus 5 over 2x minus 3 plus c. We now substitute the point 4, 3, which lies on the curve, into the equation of the curve to find the constant of integration. So 3 equals minus 8 over 4 plus 5 over 2 times 4 minus 3. Eight minus 3 is 5. So C equals 4. So the equation of the curve is y equals minus 8 over x plus 5 over 2x minus 3 plus 4. This is now the equation of the curve, and we are told that the curve also passes through the point minus 1q. So we're now going to substitute this point into the curve. So q equals minus 8 over minus 1 plus 5 over 2 times minus 1 minus 3 plus 4. So q equals 11.